Okay, everybody, so we're going to start lecture number 22, which will all be done online. So this lecture, we're going to actually go into dynamics. So up to this point, as you can see, all we looked at were fields which did not consider any kind of variation, right? So that means all time derivatives are equal to 0. Now we're going to start looking at the dynamic case where time derivatives are not necessarily equal to 0, and most likely not 0. So first, we're going to start with the continuity equation and the principle of conservation of charge. Okay, this says that charge can't be created nor can it be destroyed. Okay, so with that, we're going to start thinking about current as we already have it defined. So we have that current I is equal to basically the net outward flux of the current density vector, right? So if we have all this charge stored inside some volumetric surface, right, or some volume of charge, the current is equal to the net outward flux of the current density. And that is equal to negative dq dt, right? So that means that current is equal to the decrease of the contained charge, right? So the negative flow of charge, okay? So from this, what we're going to do is we're going to try and derive the continuity equation, okay? So as you can see right here, we have net outward flux of the current volume current density. From there, we can apply the divergence theorem, okay? We have net outward flux of J is equal to the volume integral of the divergence of J. Right? And that's just simply applying the divergence theorem. From here, we can set this term equal to the rate of change of charge with respect to time, and we have the volume integral of the divergence of J is equal to negative dq dt. Okay? But now we can go back and say, well, what is charge defined as? And can we define it in a different way that would be helpful for us? And we can. We could say that charge is equal to the volume integral of the volume charge density with respect, or over a volume, right? So from here we can actually substitute this in, and we can say that dV is equal to negative d dt rho sub v dV. Now from here we can see that this is dependent on time, right? But this dV right here is spatial dependence, right? So they don't affect one another. So from this point we can basically just get rid of the volume integral, and we can say that we could say that divergence of J is equal to the negative of the derivative of the volume charge density with respect to time, right? So as that charge flows out of some contained object, that's equal to the divergence of J. This right here is what we call the point form of the continuity equation. Okay? So we're going to use this right here, and we're going to try and get to a more useful and applicable equation. So first what we're going to notice, we have J right here, right? And we have the divergence of J. And we can say the divergence of J is equal to the divergence of sigma times E, right? And this is just using the point form of Ohm's law, okay? Now, noting that if this, whatever the volumetric surface is homogeneous, well, the divergence, the spatial dependence of of sigma doesn't matter, right? It means it's going to be the same everywhere. So we could pull sigma out of that. We could say sigma times the divergence of E, right? Okay. Then we can use Gauss's law, which says that the divergence of D is equal to the volume charge density, right? From there, we can replace this and say that the divergence of E is equal to the volume charge density divided by epsilon, okay? So now we have two separate equations here which we can use and relate to one another, right? Well, if we have that the divergence of J is equal to sigma times the divergence of E, and we also have the divergence of J is equal to negative derivative of volume charge density with respect to time, we can set these two equal to each other, and we can basically say that negative 1 divided by sigma rho v dt is going to be equal to rho v for epsilon, like this, right? Basically just solving this for sigma, and then there you have it. Okay. So now that we have this point right here, we end up with an actual differential equation. So we can solve this differential equation, right? So if I multiply negative 1 over sigma up here and divide by rho sub v, basically I have this. D rho sub v divided by rho sub v is equal to negative sigma divided by epsilon, right, dt, okay? So now you see we have a separable differential equation, right? And then we can solve for each side. So we have that ln of rho sub v is equal to sigma epsilon t plus a constant c, okay? Now if I take the exponential of each side, we would get that rho sub v of t is equal to e to the negative sigma epsilon naught t plus c. Okay, so now that we say at some initial time 0, we have a total volume charge density of, let's say, rho naught, we could then solve for a formal equation right here. So let's say that rho sub v of 0 is equal to rho naught. Well, that means that rho sub v of 0 is equal to e to the negative sigma over epsilon times 0 plus c, which would just be equal to e to the c, right? Well, then we could say that rho naught is equal to e to the unknown constant c. And then from here, we can just solve for this equation, and we can say that rho sub v of t is equal to rho naught e to the negative sigma divided by epsilon times t, right? And that's just pulling e to the c out of this part and then just setting it equal to rho naught, okay? So this right here gives us our continuity equation, right? So this says that if we have a volume of charge, right, and we give the charge a path to travel outside of the volume of charge, it will travel outside of the volume of charge at this rate right here, okay? And furthermore, you can see that we basically have a time constant here, okay? That time constant, tau, which is equal to epsilon divided by sigma, is what we call the relaxation time. Right, so if we go through 1 tau, that's when we will have about 62% of the charge we'll have left, okay? So we'll use both of these.